Hello, everybody. So today we are going to continue through section 20.2 in your textbooks. We're not even going to finish all of section 20.2. We're just going to speak about one topic, which is balancing redox reactions in aqueous acidic solutions. Because I'm keeping in mind that you've had AP exams all this week. A couple of you have an AP exam on Friday. So all you're doing today is learning about how to balance redox reactions in acidic aqueous solutions. I'll give you a couple of practice problems to work with, and you've got until Tuesday because of Memorial Day to get everything finished up. All right, so let's take a look. So also, just a little side note, these notes are all adapted from page 860 to 863 in your textbook. So if you don't feel the need to listen to me talk through the whole thing, you can just read the textbook. This video is kind of just optional for if you need to hear it kind of talked through. So that's what I'm going to do now. So far we've been dealing with balancing redox reactions. It's something that we did to get ready for the AP Chem exam, but we've only been dealing with what we call skeleton reactions. And skeleton reactions or skeleton equations only show the species that are being oxidized and or reduced. In reality, many of these redox reactions take place in aqueous acidic solutions or aqueous basic solutions, and due to that there's actually water, H plus ions, OH minus ions in the chemical equation that we haven't actually worked with yet. So today we're just going to talk about balancing redox reactions in acidic solutions. Next class we'll talk about balancing them in basic solutions. It is a different process depending on if the solution is acidic or basic, so that's something that you need to pay attention to. And again, this reading is pages 860 through 863 in your textbook, but feel free to listen to me talk through it as well. So here is your first example. I give one example. The textbook gives even more. This is a very systematic way of balancing, which means you balance all of them in the same way. So you can use this one example to balance everything else. So we're taking a reaction between the permanganate ion and the oxalate ion in aqueous acidic solution. So this is how you balance a redox reaction in an acidic solution. Your first step is always going to be to take the whole big long equation and divide it into two half reactions. And I'm going to compare MnO4 with Mn2 plus on the other side. I'm just honestly looking for like atoms. So MnO4 minus to Mn2 plus. And I'm going to pair this guy with this guy because they both have a carbon. So like atoms, C2O42 minus to CO2. We will soon learn which is the oxidation and which is the reduction. We can either go through and assign oxidation numbers now, or we can just wait and see. All right, so step 2, balance each half reaction. Balance all atoms that aren't hydrogen or oxygen first. So this is really not much different from the other types of chemical reactions in the fact that you always want to balance hydrogen and oxygen very last. So for this step, we're just going to look at all of the atoms that are not oxygen or hydrogen. In this case, it's manganese for the top one, coefficient of 1, coefficient of 1, so this guy's good. But over here, we've got 2 carbons, so I went ahead and I put a 2 in front of CO2 to balance that carbon. Again, we're not going to think about oxygen just yet. But for step 2, part B, we are going to worry about oxygens. We're not worrying about hydrogens yet, but we are going to worry about oxygens. And so we've got MnO4 minus yields Mn2 plus, and this guy has 4 oxygens. And so for every oxygen atom that we're missing in the products, we're going to add a single water. So that's why we're adding a total of 4 waters to balance. So now I've got 4 oxygens on this side and 4 oxygens on this side. This equation already has the same number of oxygens, so we actually don't need to do anything to it. Step 2C is to balance hydrogen atoms by adding an H plus as needed. So we just added a water in over here, and probably the glaring thing that you've noticed is, sure, I balanced the oxygens, but I just added 8 hydrogens that I don't have balanced over here. And so to resolve that, I'm going to add 8 H+ ions to this side of the equation. So now I have 4 oxygens, 8 hydrogens, 8 hydrogens. And this guy we don't need to worry about because oxygens are already balanced. I didn't add any waters. I don't have any hydrogens on either side, so we're not going to worry about him. And then, last but not least for part 2, part 2D is balance the charge by adding electrons as needed. So what you're going to want to do is you're going to want to see each half reaction as kind of the left side and the right side, and you want to make sure that the charge in the reactants is equal to the charge in the products. So over here, 8 times 1 is 8 plus. This is 1 minus, so I have a net charge of +7 on the reactant side. And then I have 2 plus over here, so I have a net charge of +2 on the product side of this first half reaction. I need to use electrons to balance. And so what I'm going to choose to do, this is the same half reaction coming down here, but I'm going to add 5 electrons to this side to bring down that +7. So +7 plus 5 minus gives me net charge of +2. I've got a net charge of +2 over here. As long as the net charge is the same on both sides, I'm all good. And then over here, I added 2 electrons because C2O4 2- has a net charge of -2, whereas CO2 has a net charge of 0. So I need to add 2 electrons to this side. So now I have the same net charge in my reactants or products. So now I have balanced both of my half reactions. And I stole this little summary from the textbook. A through D can be summed up by using this sequence: balance the other atoms first, then balance oxygen by adding water, then balance hydrogen by adding the H+ ion, and then balance the electrons. You always want to balance these redox reactions in aqueous solution in this order. All right, last page. All right, so finally, to step 3, we're going to multiply half reactions by integers needed to make the number of electrons cancel out in the 2 half reactions. So I wrote out my total half reactions over here. I've got 5 electrons in my first half reaction involving manganese, and I've only got 2 electrons in the half reaction involving carbon. And so, unfortunately, the nearest common factor is 10. So I had to multiply this whole reaction through by times 2, which isn't that bad, but I had to multiply this guy through by times 5. And so you don't forget to distribute it to everything. But now I have 10 electrons, 10 electrons, those cancel, and I can add the half reactions together. And this is your overall balanced redox reaction in aqueous solution. Step 5 is just to check and make sure that all atoms and charges are balanced, and you will find that they are. Hopefully that makes sense. If you need more help, feel free to send me an email, read the textbook pages. I'm going to also upload a different video of someone else showing you how to balance in aqueous solutions, just in case it helps to hear it from another person, me and the textbook, and then go ahead and try the practice problems that I am going to put up. All right, enjoy the day.